Also, to be able to understand words or more complicated letters like W, we would need multi-syllable detection, which is analysis in the time domain. And also, it would be nice if there were some alternate device interfaces. Our proof of concept version outputs to Microsoft Word. A better solution would be to have a generic keyboard output, so that it wouldn't be restricted to a computer that has Microsoft Word installed onto it. Now, here's some potential applications for the idea of speech detection on a portable device. One of which is handicapped accessibility. You can have this installed on a wheelchair, or just have this device being taken on the go. So a person that's unable to type would be able to easily communicate with the computer. Also, if the hands are required to do some other activities, such as driving a plane of some sort, like a fighter pilot, they could speak commands into the machine and using such a device.
Just go into abbreviated.
Any questions?
Thank you.
Who's the robot?
Well, it's just some generic robot.
And it's actually a takeoff of Robbie the Robot in Forbidden Planet.
Forbidden Planet, the one I was thinking of.
That's before my time. You're really dating yourself.
We won't talk about that.
Well, lots of questions. Doing an FFT on an FPGA is pretty hard. Is this a floating point or fixed point?
There are fixed point calculations.
Okay, and so you didn't have one from National Instruments? Because
No.
that would be part of your DSP library?
Actually, there's LabVIEW, the generic on-the-computer PC version, has a great suite of signal processing tools and anything you can imagine. They have a library for it. But on the FPGA, they're kind of developing this system right now, and so it's limited to basic arithmetic operations. They just released fixed point computations in this latest version.
How many points FFT is it?
We're using 256 points.
So you put that all on the chip with no trouble?
Yeah, we initially had some trouble trying to do a direct implementation, but used a sequential memory access algorithm to.
And how fast was it?
It was computed at, the clock speed on the FPGA is 40 megahertz, and the FFT took about, I think, we clocked about 70,000 cycles.
Did you see whether it would be faster to do in software?
We didn't compare it with software, but it was also, we were trying to implement this really.
You should have a point for doing so. You can implement point to it. I guess that was another question. When can we go?
Yeah, I had a question. Could you explain in a nutshell what the Melkepstrom algorithm is?
The Melkepstrom algorithm, essentially, it's Kestrel analysis. It's a form of Kestrel analysis, which is it's homomorphic speech processing, which takes the logarithm of Fourier transform of a signal, which allows you to essentially deconvolve a signal. So for speech, if you were to take every person generates kind of a pulse train in their throat, which gives a pitch of a voice, and for male, females, it's different. And then there's the convolution with vocal tract and the shape of your mouth, where your tongue is, where your lips are. And using a logarithm on the Fourier transform, you can separate those two signals. So we're looking at the shape of the vocal tract, independent of what the fundamental frequency is, what the person's kind of unique characteristics, voice characteristics are.
And then once you get this, which presumably is some sort of some sort of relationship for all of these things. I guess it's a frequency domain based kind of a thing.
Yeah.
Then you're doing some sort of pattern matching to determine whether it's an A or a B or the
Yeah.
approach.
Right. So the way we did that was we pre-computed where these points would lie in this observation space, and then we pretty much loaded this observation space into memory onto that FPGA, and we compared the inputs that are coming in with the probabilities with the observation space.
So you look for which one's best fit that pattern. How many letters did you end up testing?
Only 2 actually. But the Malkepstrom is very robust, as you can well you can't see it, but in one of the slides there are very distinct regions. But that was in the computer implementation when we were first testing. If we're able to continue this project further, we work on cleaning up the input and producing a more distinct regions in this observation space.
Other questions?
I remember that at least a couple of years ago I saw some advertisement of software that ran on Windows, on a Windows machine, that essentially you could speak to the microphone of your computer and when words were, the text was coming up. Is the goal of your project to improve on this type of software or make it more flexible? How do you compare your approach to other commercial?
Our goal for the project was to show the concept that speech recognition can be done in an FPGA. We wanted to show that since you can distinguish between 2 letters, then you can take the FPGA, put it, let's say, in a car, and control it by speaking into it. So we were more trying to just prove the idea that speech recognition can be done on an FPGA.
And also, initially, I think the software on a computer, there's one, Dragon Speaking Naturally, I think is one of the big ones. That requires almost like the top-of-the-line computer to get the kind of accuracy like that where it's conversational English. And so that's taking gigabytes of RAM, like gigahertz processors. And we're trying to take this and get it out of a large computer, get it onto a tiny chip, and kind of improve that so that you can carry around a USB stick that has the same functionality eventually as a current computer with 2 gigs of RAM and 4 gigs of processor.
Yeah, it seems like one of the disadvantages of something like the commercially available programs that you mentioned is that it requires the individual, it has to learn from the actual speech that the user is going to make. So it has to there's a training process. Does your system require a training process, or is it intended to do it without that?
Yeah, our system doesn't have a training process, but it's kind of there are kinds of pros and cons to each technique. Our technique is limited in that it will only detect speakers like us from New England area, mostly male voices, because female voices map to very different points in this observation space, unfortunately. So training does have its advantages, but for an FPGA implementation where everything's just hard set, it doesn't require any training.
And that's something that we initially looked at, and it is possible if we were to have another year or more development time to kind of eliminate the training and make more generalized probability space.